So in this second part of trigonometry, what we're going to do is going to use the trig identities to help us with proof questions. So what we're going to do now is we're going to use the trig identities to help us with proof questions. Now, when it comes to working with proof questions, your main aim is to try and, now 9 out of 10 times what you're trying to do is make the left hand side look like the right hand side or vice versa. Now I would also say it's quite common for you to take the more complicated side. So out of the two sides of the equation, one side will look more complicated than the other. And what you want to do is you want to take the more complicated side and make it look like the simplified side. And the reason why we do that is because there's more sort of room for maneuver. There's more things we can do with the complicated side to try and simplify it than it would be to make something that looks quite simple to make it look more complicated. Now, when it comes to working with proof questions, a common question that usually gets asked for me as a maths teacher is how do we finish the questions off? So you've asked to prove something, how do we put like the icing on the cake? And how we do that is by introducing a bit of Latin. Now, when you have finally proved that left hand side equals the right hand side, what you can generally do is you can quote QED, which in Latin means quod erat demonstratum, which basically means in English that which is to be demonstrated. And we tend to always find this in mark schemes, or it's another way of saying that we place this at the end of every mathematical proof to indicate that the proof is complete. So we've kind of proved what we've been asked to prove. Now, as I said, there's several ways in which we can go about in terms of these proof questions. One way is to make the left hand side equal the right hand side, but there's also that we can divide both the left hand side by the right hand side and make that equal to 1. Now, one question that usually gets asked when it comes to me as a maths teacher and from my students is, do we always need to use this? Well, in some cases, yes. Now, what I found with some of my students is if I take the left hand side, what they do is they do a few lines and then get stuck. And then they get stuck at this stage here. And then what they then do is they work with the right hand side, they get a few lines and they get to a point where these two things are the same. Now the problem is that the question asked you to prove that the left hand side, without doing that, let's go to that. What the question's asked you to do is to prove that this, the left hand side, equals the right hand side, not things in between. So if you found that you've got so far with the left hand side and then you've then decided, right, I give up, let's work on the right hand side, and you get to a point where these two sides here are equal, then what I would recommend in your solution is that you start with the left hand side, work downwards, and then once you get to this stage, then work that upwards to get to the right hand side, because ultimately what you're wanting is you're wanting the left hand side to equal the right hand side. So that's one way of getting around it. Now when it comes to our trigonometric proof, this does take practice. It's very Marmite when it comes to students. They think some students love it, some students absolutely detest it, and it just takes practice. Don't knock your confidence or feel anxious if you have to ask your teacher or have a look through mark schemes or solutions of how you get it, because it comes with practice. One of the reasons of me being a teacher in terms of how I can do these questions quite effortlessly is the amount of times that I've seen a range of questions. And if I looked at a new question, it might take me 5 minutes, it might take me 5 hours. It all depends on your frame of mind and what your initial thought is. For some people, the first thing you do works fine. For some people, it's like the 7th thing you do that gets it right. So let's have a look at this first question then. So we've been asked to prove that tan x cos x is the sort of equivalent to sin x. So here what I'm going to do is I'm just going to label this the left hand side, and here we've got our right hand side. And what I've just made a note of is the trig identities, just so I can kind of use this as a fail-safe if there's something that I'm not too sure about. So what I'm going to do is I'm going to start off by identifying which side I'm going to start with, which I'm going to start off with the left hand side. So I'm just going to start by writing that out again. Now as you can see, there's no powers involved in this, so really the only trig identity I can use is going to be the top one. So it's going to be that tan x is equal to sin x cos x. So what I'm then going to do is if I replace the tan x with sin x over cos x, and then I've still got the cos x, And lo and behold, what I can then discover is that the cos x cancel each other out, in which all I'm left with is sin x, and then I can just finish it off with QED, and there is my final answer. I don't know why I've put an equal sign there, but there you go. So there I've proved that this equals the right hand side. So one thing you might want to do is say that it equals the right hand side. Another way that you might want to do it is by using the letters of QED. So moving on to our next question, which looks like this. So it kind of looks a little bit more difficult because we've got fractions involved, but let's have a look at what we're going to work with. So again, deciding which side looks more complicated. So I would say the left hand side definitely looks more complicated than the right hand side. And again, I've got my trig identities to help and support with regards to this. So as you can see here, if I take the left hand side, it's worth just writing that without the distractions of having the right hand side attached to it, like so. So the first thing I'm going to do is, well, there's nothing much I can do with cos x over sin x because that's not part of my trig identity here. So what I can do is I can swap the tan x for sin x over cos x. Now from this, what my thinking is the fact that I've got fractions and they're being added together. So what I need to do when I'm adding fractions is make sure I've got a common denominator. So to get a common denominator, my common denominator in this case is going to be sin x cos x. So to get this fraction to have that denominator, I need to multiply it by sin x. And to get the second fraction, to get that denominator of sin x cos x, I need to multiply it by cos x. So what I've got is I've got sin squared x and cos squared x, which then, if I join those two fractions together, I get sin squared x plus cos squared x all over sin x cos x. And then if I then notice that this is also a trig identity, that sin squared x plus cos squared x is equal to 1, if I just write a little note that that's equal to 1, then that then becomes 1 over sin x cos x, which ultimately becomes the right hand side, and therefore I have proved what I've been asked to prove. So moving on to our third example. So here I've got sin cubed x plus sin x cos squared x is equivalent, can be written in the format of sin x. So again, I'm going to start off by looking at my trig identities and start with the left hand side because obviously that looks more complicated, and here I've got my right hand side. So starting with the left hand side, I start off by writing the question or that side out again without the distraction of the right hand side. And I'm thinking, right, okay, well, what can I do with this? So then I notice that I've got a cubed x, which again is not really seen in any of my identities in the red bubble. But one thing I do notice is that I've got two terms in this expression and both of them have got a sin x. So if I factorize this with regards to sin x, I get sin squared x plus cos squared x. Now also what I notice that now this bracket here is one of my identities, which is this here. So this is actually equal to 1. So what I've got is I've got sin x times 1, which just ends up being sin x, which therefore equals the right hand side QED. And there's your final answer. So in this fourth example, I've got to prove that sin squared x plus cos squared x times sin x all over tan x can be written in the format of cos x. So again, I start off by making sure I'm aware of what trig identities I can substitute in. I make a note of what's the left hand side and what's the right hand side. And I take the more complicated looking side, which in this case is by a country mile, is definitely the left hand side. So if I just start off by writing that left hand side out again, over tan x. Now I can see straight away that the expression in the brackets is also one of my trig identities. So I know straight away that that bracket is going to equal 1. Now it's always important that what I've written in blue is you are writing. Try and make it a little bit obvious as to what you're substituting in and what equals what and what cancels with what, because it just makes your work, one, easier for you to check, but also for the marker to see exactly what each of your steps are going to be. So from this, what I've got is I've got sine x is equal to tan x, and now what I'm going to do is I'm going to use this trig identity of tan x equals sine x over cos x, and I'm going to use that to replace this. So what this can be written as is sine x over cos x. Now what this then equals is sine x cos x over sine x. Now if you're not too sure about where that's come from, if I just put a bubble around this, let me just explain where that comes from. Well, that can be written as sine x divided by sine x over cos x, and the rules of when you're dividing fractions is you flip the second fraction and turn it into a multiply. So I've got sine x times cos x over sine x, and then we just multiply those numerators together, so I get sine x over cos x over sine x. So that's basically what I'm getting here. Now from this, what I also notice, I've got sine x on both the numerator and the denominator, so they cancel out, and all I'm left with is cos x, which equals the right hand side, and again you can write it off with a QED. Then moving on to our last and final example. So here we've been asked to prove that sine x to the power of 4 minus cos x to the power of 4 can be written in the format of 2 sine squared x minus 1. Now looking at this, obviously both sides look more complicated, but as I said, more often than not we always start with the left hand side. Now looking at the left hand side of sine x to the power of 4 minus cos x to the power of 4 doesn't ring any alarm bells, because there's nothing here that's related to any of these trig identities. So the question is, what do we do? Well, one thing that you should be able to spot is the fact that 4 is a square number and you are taken away. Now it may not seem obvious, but hopefully now it will do, is that what I need to do is I need to use a difference of two squares, which I've always kind of abbreviated as calling dots. Now what we need to do is, using difference of two squares, I should be able to spot that sine squared x, well, to get sine x to the power of 4, what I need to do is I need to square sine squared x, and to get cos x to the power of 4 I need to square cos squared x. One is a plus, one is a minus. So from this, these two things are going to be equal to each other, and then now using the second trig identity, which is labelled here, I know that this bracket here, so if I just get a different colour highlighter, let's go for this one, so this here is going to be equal to 1. So that's going to be equal to 1. So all I'm left with is sine squared x minus cos squared x. Now unfortunately at this point it still doesn't equal what I want it to, so what I now need to do is, because the right hand side just involves sine x, what I need to do is I need to get rid of this. I need to get rid of the cos squared x. So I look to my trig identities and say, well, is there anything that involves a cos squared x that's written something involving sine x? Well, lo and behold, yes there is, because there's this trig identity at the bottom. So I know that cos squared x can be written as 1 minus sine squared x. Now if I expand the brackets out, I get sine squared x minus 1 plus sine squared x. which I can then combine the two sine squares x together to get 2 sine squared x minus 1, which is therefore gives me the right hand side, and I've then proved what I've been asked to prove. So hopefully what I've chosen is some specific trig proof questions for you to have a look at. They do involve a range of things for you to think about, and it does take practice. As I said, these questions are not the easiest. It could take you 5 seconds, it could take you 5 hours, but persistence is key. And like I said, when you're first starting to learn these questions, don't be afraid that if you get stuck to ask for help, but also to look at the mark schemes and try and make sense of it. Try and think about quadratics, try and think about factorizing, and try and think about your end goal of, it's not just a case about like solving equations where you're trying to get one trig ratio, you're trying to make it look like the right hand side. So it's a bit like looking at the answer and manipulating what you've got to work with to make it look like that. So these some types of questions, I personally, it's one of my favorite subjects because there is nothing that gives you more pleasure than when you've spent about 3 hours trying to prove one of these questions, and finally when it gets it done, it's amazing. So persistence is key, as I keep saying. Like I said, if you've got any further questions on this particular topic, or you would like some more practice questions, feel free to drop me an email at 162maths@gmail.com.